Hello guys, I'm excited to have you once again. You're welcome to Fun with Physics. In the last lesson we looked at the application of hydraulic system. Okay, but in today's lesson we are going to consider pressure in a gas. Remember we've done something related to this, that is pressure in a liquid. They are all fluids. Gas, liquid, they are all considered to be fluid. Okay, now what you learned in pressure in a liquid is not too different from this what you're going to learn today, pressure in a gas. Okay, now look at your screen there. You see Mr. Zen. He blows a balloon. The balloon gets bigger and bigger and then suddenly bursts. Can you see him? Why does this happen? Can you explain why it happened? He keeps blowing this balloon until it gets burst. How many of you can explain why it happened? Now look at your bottom right hand side. You're going to see a similar balloon, but this time around you're going to see particles around it. Okay, now these particles here around here are actually air particles. They exert pressure outside the balloon. Okay, the pressure that air particles exert outside the balloon is otherwise called atmospheric pressure. We're going to discuss that shortly. Okay, while inside the balloon here you have air inside that also exerts pressure. Can you see the air there? The air, all the small dots there, okay, bluish dots, they are actually air particles, and the arrow there is indicating the movement of the air particles. It means inside the balloon we have air particles, or what you call molecule in your chemistry class, are moving, right? Moving here and there. The arrow indicates that they are moving, actually moving here and there. All right. Now with this, can you explain why the balloon gets burst? What do you think about the air pressure inside and the atmospheric pressure outside? Are they the same? In this case here, the one we have below where it has not burst, the pressure outside and the pressure inside is the same. Okay, the moment the pressure inside is more than the one outside, it's what? To burst. Just like what we have on the screen here. Once the pressure inside is more than what we have outside, the air, the particles will want to escape, they want to leave the object. So in that way, they will break out from the object. Okay? Now shortly you're going to see what causes air pressure. What do you think causes air pressure? Do you have an idea? What do you think actually causes air pressure? Okay, let's look at the next slide. Look at this slide. Cause of air pressure or gas pressure. We can call it air pressure or gas pressure. They're all the same. Now, what is actually happening to these molecules there? These are molecules of air and dust particles. Can you see that they are constantly bumping on each other or colliding with each other and with the wall of the container, of this container? Can you see each time they collide with the container, they bounce back. Each time one of the molecules collide, it bounces back. So if I have a number of molecules colliding, they will of course bounce back. Did you see it? Did you notice it? So particles or molecules of a gas are in constant random motion, what you call the zigzag motion. Okay, colliding with each other. Now, even though we don't see these particles, they are all experiments have shown that they are constantly in motion. They are moving and they are hitting each other. Okay, hitting each other and hitting the walls of whatever container they are in. Okay, now it's the collision with the wall of the container that causes the pressure, the gas pressure, what we call gas pressure. Okay. So it's a collision. It's Once they are hitting this, they are exerting force. Remember, pressure is force exerted in a given area. So this one exerts a force in this small area, this one exerts a force in this small area, this one exerts a force in this small area, this one over there exerts a force in this small area and the surface here. So the average pressure is what we call the gas pressure. The order of the pressure, you can get the average of the whole pressure being exerted on this, on the sides, okay? All right. So the pressure of a gas is due to the constant collision of molecules on the walls of the container inside. Okay. Now, increasing gas pressure, we can sometimes increase gas pressure. How do we do it? Now look at your screen by the side. What is this guy actually doing? He's pumping air, right, into the bicycle tire. He's actually increasing the air content in the tire. Unlike our balloon, the tire doesn't get to burst, but then or doesn't get to increase, keep becoming bigger and bigger. It stays at a certain volume at a point, but then the air inside we keep colliding, okay, with each other and with the walls of the tire as it's adding more and more air. Okay, so a bicycle tire does not keep on expanding like a balloon does. We've said that. Pumping up a bicycle tire increases the gas pressure inside the tire because you have more air inside, more air added, which increases the rate of collision. So in a system where you have more air, you expect to have more particles or molecules colliding with each other, hitting each other or hitting the walls, isn't it? All right, now what do you think about the pressure and volume? What do you think about pressure and volume? Now this is a case where you have, before I started, a case where you have a volume, a container sealed up, then a piston, then this tiny things here indicates or symbolize molecules. Okay, they move about randomly. Can you see that? In a zigzag manner, hitting the walls, right? And we say because they are hitting the walls, they are exerting what? Pressure on the walls, isn't it? So the pressure is actually due to the collision, the force they use to hit those areas, those walls around. Now, what's the relationship between pressure and volume? What will happen to this, to the pressure inside when I decrease the volume? Okay, let's see what will happen. Let's try to decrease the volume and see what will happen. So notice that the temperature is maintained at 9 degrees. So what do you notice? What did you notice? All the particles are crowded together in a space, isn't it? So what did you notice about their movement, their kinetic energy? Are they faster or they are slower? Of course they are slower, isn't it? Of course they are faster, sorry. Of course they are faster, isn't it? Yeah, they are faster here. Now how about the collision? The rate at which they are hitting the walls. Is it more frequent or is it less frequent? More frequent or less frequent? Here, is it more frequent or less frequent? How about in this case, more frequent or less frequent? Of course, here it's more frequent, isn't it? So we expect, since the collision here is more frequent, we expect the pressure here to be higher, right? Because they're hitting it more frequently. But here, less frequently, they're hitting the walls less frequently, so we expect the pressure to be lower. And remember what I told you about pressure. Pressure is actually caused, gas pressure is actually caused by particles or molecules colliding with the walls of the container or the walls of the vessel. Okay, so here I have more pressure because the collision is more, but here I have less pressure. So I have less pressure when the volume is bigger, but when the volume is smaller, I have more pressure. So small volume, more pressure, big volume, less pressure. Do we understand? So when you have big volume here, that's the relationship. You expect to have less pressure in the system when the volume is bigger. where you have more airspace, so you're going to have less pressure. But when you have less airspace, you see that the particles are colliding more, so you have more pressure here. Okay. Now pressure. Now we are also going to investigate this before we do that. Now look at the system here. What you have here, similar to what we did before. Here in this case, the piston is being moved, pushed inside, and the air particles are being compressed. That means we are decreasing the volume of the air particles here. Okay. So we want to really look at critically what will happen. Will the pressure be increased? Okay, we've actually found out. How about when you decrease the volume, when you make the volume half the volume it was before? What will happen to the pressure? Now look at it. When you make the volume half the volume of what it used to be, the pressure will increase, but we don't know how much. Now look at this. The second picture here will show you how much. So here in this case we have the volume as 1 liter, the pressure is 1 atmosphere. But when you make the volume, decrease the volume to half of what it used to be, that is 0.5 liter, you can see that the pressure here is doubled. Okay, so it means in a system or in a container, if you can decrease the volume to half of what it used to be, the air particle in that container will exert twice the pressure it's used to exert before. If the pressure, for instance, exerting the container is 1 atmosphere, when you make the volume half of what it used to be, it's going to become 2 atmosphere. Do we understand? Okay, now the relationship, this kind of relationship where when a quantity is doubled, another one is halved, or vice versa, is called inverse proportion. Okay, you double a quantity, you increase the quantity by 2, like the volume, you double the volume, and then the pressure is going to be halved. Or you double the pressure, you expect the volume to be smaller. Okay, so that kind of relationship is what we call inverse proportion. Okay, so when a quantity is doubled, another one is halved, or vice versa, we say that the two quantities are inverse proportion. There are many cases where we have inverse proportion. Can you think of such cases where when you double one quantity, the other one become half of whatever it used to be? Okay, so think of, there are lots of cases, and we also have cases of direct proportion. This case we are discussing today is inverse proportion case. Okay, in direct proportion, when you double something, one quantity, the other quantity is also going to be doubled. But in this case, inverse proportion, you double one quantity, the other one will become half of what it used to be. Right? So the pressure is inversely proportional to the volume here at a maintained or constant temperature. So temperature is what we actually control. In an experiment, you have to maintain something, you have to control something when you're observing two things, the relationship between two things. Okay, so we write this relationship this way mathematically. P, this symbol here means proportional to 1 over V. 1 over V means it's inverse. Of course, when I say find the inverse of something, it means I'm asking to find 1 over that thing. So P is proportional in an inverse way with volume. Okay, it means if I should double P, I'm going to halve the volume. Sorry, if I should double the pressure, it means the volume will be half. For me to double the pressure, I need to take the volume of whatever the container is to become half of what it used to be. Okay, so for me to reduce the pressure, I need to double the volume. Okay, to reduce the pressure by half, I need to double the volume. That's what it means. I hope we are following. I hope we understand. Do we have any problem? relationship between pressure and volume. Now we can actually study this in the lab. Okay, we can actually keep reducing the volume and taking the pressure in each case. So here the volume is 50, the pressure is 1.2 atmosphere, and here the pressure is, the volume is 37.5. Okay, sorry, the volume is 1.2 Newton per meter square. So here the volume is 37.5 meter cube, and the pressure is 1.6, and so on and so forth. So when you take this, perform this experiment, and you take this reading, and you get to plot the graph of pressure against volume, you're going to get a graph like this, a curved graph. Okay, that means any time you see a curved graph like this, the relationship between the two quantities here, okay, the dependent one and the independent one is inverse proportion. Okay, so in this case we have a curved graph. Okay, but if you want to obtain a straight line graph, all you need to do is to plot pressure against 1 over V. Okay, anyway, this is for another time, for practical class, but I want you guys to have a clue of how the relationship is like, okay, and how the graph will look like. Now to atmospheric pressure. Now earlier in the slides, let's take you back to the slide. I told you that the pressure acting outside here, the pressure due to air outside here is called atmospheric pressure, isn't it? Okay, so we can say that the pressure exerted by the atmosphere, that is the air around us, is what we call the atmospheric pressure. Alright? So air around us actually exerts pressure. Remember, air around us constantly bump on us, constantly hits us from all directions. So the pressure is called atmospheric pressure. We don't get to feel it because the pressure is being balanced by the pressure in our body, in our blood, in our system. Okay, it's being balanced. Both of them are being balanced, so we don't get to feel the atmospheric pressure. We have more air close to us than away from us, as gravity pulls the air towards us. So we expect atmospheric pressure around us to be higher than atmospheric pressure above us. For instance, if you move a little bit, let's say to a mountain, you will notice that the air there is thin. That is, you don't get to have much air as what you have here. So it's like gravity here from our picture here constantly holds most of the air close to us, close to the earth. Okay, so the pressure, the atmospheric pressure that is exerted on us close to earth there is more than the one exerted on items that are far away from us, like items on the mountain. Okay, so that's why anyway, before I tell you about that, let's quickly look at before I tell you some of the consequences of atmospheric pressure, let's quickly look at atmospheric pressure decreases with altitude. Okay, like I told you earlier, if you go up high the mountain, you notice that the pressure there is low because you don't have much air there. You see, the number of air here is not as much as what you have here. Okay, down. So you keep going up, you have low pressure, but down you have high pressure. Okay, so atmospheric pressure at sea level is greater than atmospheric pressure high up a mountain. Okay, I've already explained that. So because we have more air close to us than at high altitude. Now for this reason, these are some of the consequences, these are some of the reasons, okay, the results of having this atmospheric pressure. For this reason, mountain climbers carry oxygen tank when they climb high mountains like Mount Everest. So if you happen to you love climbing, and maybe you love climbing and you want to do that, have a climbing spree or exercise tomorrow, make sure you go with your oxygen container. Okay. Now the essence is that up there in the mountain, the air is thin. You don't get as much oxygen as you need. Okay, the air is not that much, so you need to carry your own extra oxygen. Not only that, the pressure there is low. Of course, the pressure there is low because we don't have much air there bumping on you. Alright, so you need to balance the air inside your lung, moving into your lung, and the one in your system. Alright, now number 2, a can is crushed when air is completely removed from it. Now look at this picture here by the right hand side of your screen. Can you see what's happening to this can? The can is being crushed naturally. So when you try to remove all of the air in a can, in a container, you can do that by you put some little water and then heat it up, open it up so that they can move out, and then seal it up again. Alright, the moment you seal it up, the pressure inside, the air inside will be low because the pressure inside will be low because the air inside, the amount of air there is almost zero. Okay, so when this happens, the pressure outside will what? Crush the can. Okay, it's like you don't have any resisting pressure, any balancing pressure from inside. So that's another consequence. Another one is your ear pops during flight to equalize air pressure with the environment. Okay, during flight, the pressure outside, the air outside and inside your body is not the same. So what happened? Your body lets out air from your ear, okay, to equalize the pressure. So you can see this lady here feeling slight pains in the ear because of the pop. Okay, now there are other consequences, there are other effects of atmospheric pressure. There are other effects. So as a closure, I want you guys to list other effects of atmospheric pressure. Go to Google Classroom and list them on the comment section. Okay, now you can also try this. Why is atmospheric pressure in space, sorry, not in space equal to 0? That is almost zero pressure. Why don't we have pressure? Why is the pressure in space so low, almost equal to 0 or equal to 0? Why is it equal to 0? So you should have a question mark here too. Now, what happened to a man that moves to space where the atmospheric pressure is 0 without a space suit? What do you think will happen? If I decide to go to space now without my space suit and the pressure is 0, what will happen to my body? What will happen to me? Guys, I want you guys to think this through and comment on the comment section of my wall on Google Classroom. Okay, thank you. See you some other time.